So our next speaker will be Josep Àlvarez Montaner, and he'll tell us about Bernstein's inequality and holonomicity for certain singular rings.
Okay, so thanks a lot to the organizers for the invitation. So I want to report some work with that is joint work with some good friends in Daniel Hernandez, Jack Jeffries, Luis Núñez Betancourt, Pedro Teixeira, I think is over there, and Emily Witt. And by the title, probably you will see that what we want to deal is with some basic notions on the theory of deep modules, with the twist that we want to deal with singular rings, not only in the smooth case. And there is this certain singular rings that means that we cannot reproduce the theory for any singular ring. So I will start just recalling the basic theory on the modules of the polynomial ring in characteristic 0. So you can open Coutinho's book at this point and try to refresh everything. So we start with the polynomial ring of a field of characteristic 0. Recall that delta I is going to be the partial derivative with respect to the variables, and the ring of differential operator is just the Bayes algebra. So it's the R module generated by this delta 1 delta n. It's not commutative, but it's Noetherian, so it still has some good properties. So one of the first things that one learns in any deep module course is that the ring of differential operators is filtered, and the associated graded ring is a polynomial ring into n variables. But in this situation, we have like two natural filtrations. The order filtration that essentially is associated to the degrees 1, 1. So I mean the degree of the variables xi is going to be 1, the degree of the partial derivatives is going to be 1, and here I am just using multi-graded notation. On the other hand, we have this Bernstein filtration. Oh, sorry, I'm saying the opposite, right? So this is 0, 1. So the degree of the variable x is 0, and the degree of the partial derivatives is 1, and the Bernstein filtration is this 1, 1. So both are increasing filtrations that are multiplicative, exhaustive, but the main difference is that the order filtration is a filtration by R modules that are free of finite rank. Meanwhile, the Bernstein filtration is by K vector spaces that are finally of finite dimension. Okay, so the Bernstein filtration is exclusive for the polynomial rings. The order filtration you can work for formal power series ring, but the Bernstein filtration has some nice properties that we will see later on, in the sense that some of the proofs of the main results, when we use the Bernstein filtration, gives you a more simple proofs of many things. So we forget about the order filtration and we focus on the Bernstein filtration. And this is the point of view of Coutinho's book. Okay, so then we take a finally generated the module, and we consider a filtration that is compatible with the Bernstein filtration. And we say that this filtration is a good filtration whenever the associated graded module is a finally generated graded module over this polynomial ring into m variables. Okay, so this is one of the definitions of good filtration. If you go to the non-commutative algebra world, they will say that, well, good filtration is a filtration that is associated to the generators of this module and is somehow natural to just consider this standard filtration. So we want something that is equivalent to a standard filtration. But in any case, for us, we start with a finally generated module with a good filtration, and we have this notion of dimension and multiplicity. But since we are working with filtration of K vector spaces, we just define the dimension by the growth of the dimension of this filtration. So we have these equivalent ways of defining the dimension, and then the multiplicity is just the limit of this guy. Okay, so in here, I am saying that this is the dimension of the module, but indeed what I am meaning is that this is the dimension associated to this filtration. In general, different filtration may give you some different dimensions, but this is the good filtration, this is standard filtration, any other filtration is dominates this filtration. So in some sense is a canonical way of giving a filtration. Okay, so Bernstein inequality says that when we have a finally generated D module, the dimension is bounded below by n, that this is nothing but the dimension of the ring. Okay, and also we may say that this is smaller or equal than to n, that this is the dimension of the ring of differential operators. And using Bernstein filtration, we have a very simple proof of this result, because this is based in the following morphism. We can define the following morphism that goes from this piece of the Bernstein filtration to the morphisms from the filtration on our module, G2I, simply from an element in here, this goes to this morphism from here to here, and that sends an element to delta P. Okay, so recall that these two filtrations are compatible, so this is well defined. Okay, so a key point in the proof is that this morphism is injective. But I will explain a little bit more later on about the injectivity of this morphism. And then, well, we end up that the dimension of BI is smaller or equal. Well, here we have these morphisms. So the dimension of GI times the dimension of G2I. So this leads to the dimension of the ring of differential operator. This gives you the dimension of the module twice. And this gives you more or less the proof of Bernstein's inequality. So as I mentioned, the key point is that this is an injective morphism. Okay, so the class of holonomic D modules are those of minimal dimension. For example, we have that the polynomial ring itself is a holonomic D module. The localization at any element is a holonomic D module. The local cohomology modules are holonomic D modules. And maybe you may recognize this thing that has its importance in the theory of Bernstein-Sato polynomials. Okay, so proving that this is a holonomic module gives you a very simple way to prove the existence of Bernstein-Sato polynomials. And here I am using the polynomial ring in coefficients in this fraction field. Okay, one of the main consequences of having a holonomic D module is that the length of this D module is finite. And this was used by Ljubeznik to prove some finite properties of local cohomology modules, like the set of associated primes is finite or the Bass numbers are finite. Okay, so when we move to positive characteristic, so I am assuming that R is a polynomial ring over a field of positive characteristics, and sometimes I'm going to just assume that K is perfect, not right now, but in many situations. We have a theory that is parallel to the theory of holonomic modules developed by Gennady Ljubeznik, and he introduced these F-finite F modules that essentially is a module with the action of the Frobenius map. He proved that the length as an F module of such a F-finite F module is finite. Indeed, he also proved that these modules have a natural structure as a D module, so the length as a D module is also finite. And he reproduced exactly the same properties in positive characteristic as in the characteristic zero case. The set of associative primes of a local cohomology is finite, the Bass numbers are finite. This was already proven by Huneke and Sharp a few years before. Okay, but even if we are in the setting of positive characteristic, we know that the ring of differential operators can be constructed using a Grothendieck approach. So in this setting, the main problem is that the ring of differential operators is defined using these higher differential operators. Okay, so the main problem here is that this is not Noetherian. So Babula, even if we are in a setting that this is not Noetherian, studied the question about defining holonomic modules in this situation. So in his case, he considered the ring of differential operators with a filtration that is a natural extension of the Bernstein filtration to this setting. Even if this is not Noetherian, you can do that. Use the same definition or introduce this definition of dimension, and I have to point out that this, in general, this is not the Gelfand-Kirillov dimension of the ring of differential operators. If we think that this is the dimension of the ring of differential operators, this is 2n, but the Gelfand-Kirillov dimension is n. So one has to be careful with this notion of dimension in this setting, but he reproduced the same arguments. He started with a finally generated D module with a good filtration in the sense that it depends on the filtration of the ring and using the generators, and he proved Bernstein's inequality in the same way. So here I am just pointing out that this is the dimension with respect to this filtration. You can make it a little bit canonical when you work with this finally generated D module. And in his case, holonomic D modules are finally generated modules with minimal dimension, and we also have the same consequences on the length. Okay, the problem here is that we have situations where there exist non-holonomic modules of minimal dimension. This is a weird example that he proved. And also Moti Katzman, Gennady Lubeznik, and William Zhang gave examples of holonomic, well, you know that holonomic modules are closed by extension in characteristic 0, but not anymore in positive characteristic. And also they noticed that the multiplicity may not exist, since this limit may not exist. Okay, so let's go to the ideas of Babula that one can extend to a very general situation. So in general, we are going to think about the ring of differential operators, but we can think of any filter K algebra. Okay, so in our situation, we have a K algebra that is filtered and a module over this K algebra with a filtration that is compatible with the filtration of A. Recall that we have this notion of dimension, but you will notice that here we are using lim sub to avoid all the problems that we had with the case of positive characteristic. Okay, so and a key idea that is already in Babula's work is this notion that we coin as this filter K algebra as being linearly simple if they satisfy this property. Okay, the idea is that, for example, in the polynomial ring case in characteristic 0, this situation can be described using the commutator of differential operators in an iterated way. Okay, so the lemma, the key lemma to prove Bernstein's inequality in this setting is the following. Recall that we had such a morphism. Okay, and to prove this, assume that this morphism is not injective. This is the key point that I mentioned before. So assume that we have that sum of this guy is 0. So we had from delta to this psi delta that goes from here to here. And okay, so this means that when we apply delta, put it here, when we apply delta to this G whatever, this is going to be 0, but we have that inside we have Fi, Fci, Gi. So this guy is going to be 0. So it means that when we apply Ci delta Fci Gi, this is going to be 0, but we have 1 in here. So it means that this has to be 0. So we get a contradiction with the assumption. Okay, so this condition is a key condition to prove the injectivity and reproduce the proof that we can find in Coutinho's book. Okay, and then, okay, we can reproduce Bernstein inequality. We also have this bound on the multiplicity given by the multiplicity of the filtration on the ring of differential operators. And we coin the term holonomic in this situation as something of minimal dimension. Okay, here I should mention that we are asking a lot of extra conditions on the dimension of the filtration and the multiplicity that we got for free in the polynomial ring case in characteristic 0. So in this situation, we don't have it for granted, so we have to ask for these conditions. Okay, so what we also were able to prove is that holonomic are closed by submodules and quotients, not by extensions, and these modules have finite length. Okay, and if we think in the case of ring of differential operators, we have that the local cohomology modules are holonomic, so they have a finite set of associated primes. Okay, so let's move to the case of singular varieties. We can define the ring of differential operators by induction on the order. For example, when we have a quotient ring, everybody knows that we have this description depending on the differential operators that stabilize the ideal I. In our situation, we are going to consider I being homogeneous. So we have a graded K algebra. And what we want is to have a filtration that mimics the Bernstein filtration that is linearly simple. And maybe we also want these extra conditions that are going to be nice. So this is what we denote as the Bernstein algebra. Okay. So the first step is to give some filtration. So we propose to give this generalized Bernstein filtration that depends on the degree of the differential operator and the order. The order is clear. The degree is just because this is a graded ring. We say that delta is homogeneous of degree D. See, it satisfies these conditions. Okay, so in the polynomial ring case, the Bernstein filtration is just the Bernstein filtration for A equal to 2. Just because the degree of the partial derivatives is -1, and the degree of xi is equal to 1. Okay, so this is very natural. So in general, if the polynomial ring, for example, is not a standard graded, we need this extra assumption that this is important. Okay, so let's go for these Bernstein algebras. I mentioned that if we have that the ring of differential operators is linearly simple, this means that we have Bernstein's inequality. Okay, and we give some sufficient conditions depending on this invariant introduced by Holger Brenner, Jack, and Luis, that is defined in this way, that ensures us to have these extra conditions. Okay, one has to work a little bit, but if we have this property on the differential signature, this gives us the dimension of the ring of differential operators, or the Bernstein filtration is twice the dimension of the ring, and the multiplicity is finite. Okay, so examples of rings with positive differential signature. In characteristic 0, we have the ring of invariants of a finite group. And in positive characteristic, if we have a ring that is F pure, then the differential signature is positive, strictly positive, if and only if this is a strongly regular. So these are still results of Bernard, Jeffries, and Núñez-Betancourt. So the main result of our work is that when we are in characteristic 0 and we have a ring of invariants by a finite group, then the ring of differential operators is linearly simple. So we also have that this is a Bernstein algebra and we get all the consequences. And in positive characteristic, we have this notion of F finite representation type that in general, it doesn't need to be strongly regular. So we need this extra assumption. And under this extra assumption, we have that the ring of differential operators in this setting, this is linearly simple. And in the characteristic 0 case, we have this extra result that I don't want to explain the meaning of differential direct sum. And just for the records, this notion of FFRT rings was coined by Karen Smith and Michel van den Berg, and it depends on this decomposition. Okay, so I want to stop here and say thank you.
All right, thanks, Josep. Are there any questions? Maybe I'll start with a question. So I was curious if you know any other examples of linearly simple rings besides rings of differential operators.
Not really. I mean, we didn't try any other example. I would try to think.
Yeah, we didn't think about this, but yeah, I was wondering if maybe you came across something there at some point.
I would likely start with Ore rings. So Ore extension is like you are adding derivations and other stuff. Maybe in this situation, you may try something like the ring of the Frobenius algebra is one example of Ore ring.
Oh, I see.
So you can mix adding the Frobenius and maybe a Cartier operator, and you can also add differential operators over there. This may resemble a ring of differential operators, but I'm not sure if one can get this type of results.
Okay, yeah, thanks.
Can I ask a question, Jack?
Oh, please do.
Yeah. Hello, Josep. Josep, in the theory of the modules in characteristic 0, you have a strong add from geometry that comes from symplectic geometry, right? So you have Poisson brackets, etc. Actually, you can even give a proof of Bernstein inequality just using the involutiveness of the characteristic variety. I wonder if there is something analogous to that in positive characteristic.
As far as no, I mean, indeed, there are 3 different ways of defining a holonomic model, right? In terms of the characteristic variety, in terms of the computation of dimension, or even using homological algebra, like historically on the X. In positive characteristic, what you have is this differential operators defined by Berthelot, and he announces some kind of characteristic variety depending on the level of the ring of differential operators. But it's something that he only announced, but he never proved or gave the whole results. But the ring of differential operators in his case is a little bit different. So our ring of differential operators, the different pieces of the level computation is a quotient of this ring of differential operators at level E. So in the ring of differential operators is a limit of differential operators of level E. It each of them is some kind of Bell algebra, and he constructs some kind of limit characteristic varieties for each level. So I'm not sure if we can compare our construction with his construction, because he didn't prove anything, he just announced. Well, I don't know
Okay.
if in relation.
Okay, thank you.
Are there any other questions for Josep? Well, if not, let's thank him again. And yeah, we'll take a short break and resume in 5 minutes.
I will